This conference will now be recorded.
All right, good morning and good afternoon, everyone. Brian Goffel here, Weather Service Office of OBS. Want to welcome you to today's Satellite Book Club presentation. Before we begin, just want to remind you, you've probably heard the session is being recorded so that others might hear the presentation who are unable to attend today. We'll have Q&A as usual after the presentation, and we're encouraging you as usual to post your questions in the chat room, and the team here will be fielding them from here. This week, the presentation will be facilitated by Randy Bowers, meteorologist at WFO in Norman. Thank you, Randy, for doing this with us. And we're always looking for future presenters. There's quite a range of topics across the domain of satellite products and data exploitation and application of the forecast process. So we would welcome your input to future presentations. The training team can help create the training materials that might be unavailable. Brian Mata has been working with Office of OBS and others to do that. So Brian Mata can be contacted about that. Thank you very much, Brian. And also, thank you to the many people who make this happen, including the OCLO, our partnership with the GOES-R program, the JPSS programs, and STAR, Office of Central Processing, and TELRES team here who actually puts these on, and Joe Zajic, Lee Biley, Lewis, and co-workers. I want to introduce Jason. Jason Jordan has been a meteorologist with the Weather Service for 26 years, and most of that time in Texas. His interests are in radar meteorology and severe convective storms. As a senior meteorologist at WFO Lubbock, Jason became involved with lightning research at Texas Tech. This research has allowed him to gain experience using lightning mapping array and how total lightning data can be used at a WFO. Once the GLM instrument was placed in orbit with GOES 16 and 17, the work continued, and it now focuses on how all lightning data sets can be integrated into weather service operations. Jason recently moved to Colorado as one of the newest members of the Forecast Decision Training Division, working on forecast process-related training, but he'll remain in lightning-related meteorology and how this ties into the forecast process. So with that, we want to welcome Jason to the Satellite Book Club and welcome all your listeners, and we look forward to your presentation.
Thank you very much. How do I sound?
Loud and clear, thank you.
Good deal. Well, we're going to take a look at more of kind of how the GLM works, because that will impact how it's used in operations. There's plenty of training already out there about the GLM, how it looks at lightning, how it takes that data, processes it, and then gets it into the grids that we see in the Weather Service, and now we're starting to see available online through other websites. The GLM isn't the first lightning mapper that's been in space. There's a long history that goes back, and basically it moved from proof of concept, can we see lightning in outer space, to where, okay, we can see it, so how do we use that for some of our projects that we're working on, and then it started to be used in research projects. Most notably, when I started my undergraduate degree was the TRIM satellite, and using the lightning imaging sensor on that. But all that data has been posted in. The satellite was up there collecting it, transmitting it to the ground, then it had to be processed, and so any of that data that you were looking at with those previous lightning detectors took a bit of time, and they weren't available in real time in most cases. So the GLM is really the first in weather service operations where that data arrives in nearly real time. I say nearly because it takes about 20 seconds for it to be processed on the satellite, transmitted to the ground, and then go through the ground network to be processed into the grids that we see in AWIPS. And it's not the same lightning data that we're used to looking at. We'll take a look at that here in a minute, but a lot of the training really hasn't described what the sensor limitations are and how that can impact what we see in AWIPS and out in the field. Now, I'd mentioned that this is kind of the first that we've seen in the Weather Service. We're all used to looking at ground data. The NLDN has been around. That's kind of the first generation that we've seen in the 80s and 90s. And this great slide was developed by Dr. Eric Bruning and was presented at the GLM science team this meeting. And it does a really good job of showing where we are now in basic kind of lightning science and how we detect lightning. You've got a bunch of ground-based networks, the Worldwide Lightning Location Network, and the NLDN that we're familiar with, and the Vasala GLD 360 world merge data. Earth Networks has their own network, and we're starting to get more research instruments out there like lightning mapping arrays that can see all this different kind of information from lightning. Now we've got the GLM that's in orbit, and it's kind of seeing a little bit of what all these other sensors are. This image on the right kind of shows how all these are being seen. The colored dots that are on the rainbow are what a lightning flash looks like in an LMA. And so we're actually able to see the channel paths and the information on the timing of how this lightning occurred. We see the ground-based detection in all the networks, or most of the networks. You see intercloud flashes that were starting to be displayed at AWIPS. But then you still have this optical energy that's going out and now is getting sent up to the GLM in orbit and can be detected from there. So what can you see and where? The ground-based networks do a really good job of giving you the lat long points within several tens to hundreds of meters, depending on a bunch of factors. We're starting, like I said, to get some of the cloud information in, mainly from Earth Networks because of how their network is developed and the sensors are, more so than the GLD and Vasala data. And we do get some flash characteristics. We're used to looking at the positive and negative polarity in AWIPS. We can drill down to at least minute data and how that averages with the time. But if you dive deeper into the data inside of AWIPS, there's oodles of other data that's in there. We can look at the polarity, not just the polarity, but the intensity, the number of sensors that have detected the flash. For the intercloud flashes, there's actually information on the altitude that all that is in. So we can see some of the flash characteristics and have some of that stored, but we just can't access it easily in AWIPS. So now we go to the space base with the GLM, and it's not the latitude and longitude of the ground strike. You're still looking at the 8 by 8 kilometer grid directly underneath the satellite, and that expands as you move out from the edges to a 14 by 14 kilometer grid. And you have to remember that it's projecting that from somewhere in the cloud to the satellite. So you're not actually looking at where it hits the ground, it's somewhere in that pixel as that energy goes to the sensor. 99% of it is cloud only. And I say 99% because every once in a while you'll have something like a sun glint off of a solar farm or a stray radiation strike that hits the sensor followed by some noise, and the filters that are on the GLM actually think that that's a real flash. I say that last case because that recently happened up in the Great Lakes. But we get a bunch of flash characteristics that we don't get from the ground-based networks. We get flash extent density, total optical energy, average flash area, and that will soon be minimum flash area once we get the new upgrade with the Tower S package and some changes in the ground-based processing. So here's a map of what the detection efficiency looks like for both GOES 16 and GOES 17. It was provided by Dr. Ken Cummings, and again, he presented this at the GLM science team meeting. So on the left side is GOES 17, on the right side is GOES 16. Going in the row, the best nighttime detection efficiency is at the top, and daytime detection efficiency is at the bottom. So you can see just in general that at nighttime, as is expected, the detection efficiencies are higher. At nighttime, they decrease because you have to overcome the amount of light that's hitting the clouds that are generating lightning. And you can see again that directly underneath the satellite is your best detection efficiency, and then it falls off as you trail off towards the edges of the sensor. The reason I bring this up is that if we look at it across just the central part of the United States where the two sensors overlap, you can see that it's still not 100%. And this is a limitation because of the way that the sensors are located in orbit and the sensors themselves. The best that you can get at nighttime for GOES 16 and 17 is up around 60 to 70% across the northern plains and into the northern Rockies. And it tails off and increases as you go down into northern Mexico and the central and southern plains. Daytime, unfortunately, that falls off even lower, and you probably are in the 20 to 40% range up here in the northern part of the US, and still only around 60 to 70% down into the Southern Rockies. And again, this is for a best case scenario. And as we all know, meteorology is rarely best case. From a convective point of view, a recent paper that was released by Dr. Rutledge and his co-authors in the Journal of Geophysical Research and Atmospheres does a really good job of looking at cases from northern Colorado and northern Alabama, and lets it look at how the GM looks at these storms and some of the factors that may have resulted in different detection efficiencies and different amounts of flashes being detected in those two areas. It does a really good job of explaining what some of the best case scenarios impacts would be in a convective environment. But a better way to look at that is with this example that we had in Lubbock. Nice flash that came out of the side of a thunderstorm. This was in June of 2017. And two things to notice is that there's just a lot of heavy rain in here. This flash comes out kind of on the northwest side of the thunderstorm. As the flash progresses back into the cloud, you can see kind of the outline of the updrafts and some of the cumulus that are going in there. But you notice here on the right side of the picture, there's just not a lot of energy or light making into that. This was right after GOES 16 had made it on orbit and the GLM had been turned on. I was at work and noticed that, well, we picked up this flash in the LMA. You can kind of see it here in this little green extension off to the north of the storm. The thing to remember is that at the checkout period, the satellite was a little bit further west. And so if you're looking at this picture, it's kind of back behind your head. When we went back and looked, I sent all this information to Dr. Bruning at Texas Tech, said, hey, we saw this flash. I caught it on video. It's in the LMA. Did the GLM see it? And it didn't. One of the things it could be is that in this picture, you can see quite a bit of the precipitation in there is absorbing a lot of the light energy. We don't know how much is in the cloud, but I'm sure that because of the intensity of the precipitation below, that this updraft was fairly strong. And so even in this case scenario where the lightning went out into clear air behind the storm, all that optical energy didn't make it to the satellite and it wasn't detected. A more recent case, it was here back in August with the Pine Gulch fire in western Colorado. Up here in northeast Colorado, there was actual precipitation taking place. The GLM did manage to detect a flash associated with this ground strike in the National Lightning Detection Network data. And over here is the Pine Gulch fire. You can kind of see the red. This is a 3.9 micron imagery satellite, so that is actually the fire with this nice plume coming off of it. And the Grand Junction office posted on Twitter some pictures and video of lightning taking place in this convective plume. Fast forward to 12 minutes later, and sure enough, the NLDN picked up a positive flash associated, a positive ground flash associated with this pyrocumulus. We're still seeing the GLM pick up flash here with this slight precipitation in northeast Colorado. Overall, cloud temperatures look somewhat similar. The cloud tops up here in northeast Colorado are a little bit colder than the ones associated with the pyroQ. But again, no GLM flash. And the cloud-based sensors did show that there was cloud activity, cloud flashes with this pyroQ. So why didn't the GLM see this one? Probably again because it wasn't best case. You're having to send all that optical energy through smoke, through soot, through ash, which is dark and probably absorbs a lot of the energy. And then on top of that, you've got a pyrocumulus that probably has some precipitation and ice particles in there as well. So again, even in environments where we have lightning, it may not be best case to get that energy back to the GLM. Well, what happens if the GLM is working and we have a storm that's moving across, a large area of storms that's moving across the Central Plains? This squall line happened overnight on April 29th, and we were sitting at work, and I was using this kind of to train another person, a new employee in the office on the GLM. So what we have here is we have the flash extent density here in the top right, the total optical, or excuse me, the average flash area in the bottom left and the bottom right. The only difference is the color tables, because I was showing how you can pull out some more data depending on what your color table is like. And then the ground-based flashes are also overlaid on that as well. Well, if you watch this loop with time, you start noticing about halfway through the frame, there's these large dropouts that are taking place in the flash or the average flash area. Hard to tell if that's happening up in the flash extent density, but it looks like there could be some hints there. So what's going on? it looks like that this data is just missing. If you were to sample it, it would just, nothing would be there. And so out of curiosity, you know, I'm like, this is unusual. So I posted that picture on Twitter and finally got a response from one of the scientists on the GLM team saying that what was unusual about this MCS was that it was oriented along the right axis from southwest to northeast, which placed almost all the lightning activity reaching the GLM into a single output channel that it measures. So that means that it was pushing on average 800 events per second reaching the GLM. And when you got above that, in those peaks in there, it caused the data to overflow in the GLM. And even though the GLM is set up to try to handle the best case scenario for detecting lightning, you can still have cases in Mother Nature where it's like, yeah, well, that's not the case. We've got this one kind of on the tails of the meteorology, the tail of distribution. And in this case, the sensor overflowed 2,700 times during this event. If you were using this in real-time operations, what would you think? Well, is this a problem with the processing? Is this a problem with the data coming through into AWIPS? Or was the case in this event, it was actually a problem with the processing on the GLM itself through the ground-based network? So some things to remember. No sensor, regardless of whether you're looking at ground-based or space-based, has 100% detection efficiency. Some do get close. And the key thing is that you need to look at all this data together. Now, in the era of DSS and stuff, knowing the ground locations of lightning strikes can be helpful, especially for events and outdoor venues. But maybe what's more important overall during operations is to look at the trends, to know, well, what I'm looking at here, I'm seeing these holes in the GLM data. Why are these dropping out and I'm still seeing ground data? Or vice versa, I'm looking at the GLM and it's showing all this activity. Why am I not seeing in any of the ground-based networks? So that's where you can use it in operations, is to know, well, the GLM can fill those gaps in if I'm seeing something wrong, and the other way around. Ground-based networks may be able to help me see something that I'm missing on the GLM. So this is an example that I worked with Dr. Bruning again, and this is a plot of just 2 minutes of lightning data over my house in Lubbock when I lived there, of all the lightning data we could get. Top frame, you have lightning flashes going from left to right in time, so the blues are beginning of the time period to the oranges and yellows at the end. We have the ground flashes plotted down here at the bottom, and the cloud flashes detected by the ground-based networks, kind of these X's and pluses here at the top. Overlaid behind that are the detections from both GOES 16 and GOES 17 GLM sensors. So starting off early on here, we have a flash that was, kind of low in the storm, below 8 kilometers. It was produced 2 ground detections in the 2 ground-based networks that we get in AWIPS. And it looks like both 16 and 17 saw that flash. The next one didn't produce a ground flash in the LMA and didn't detect anything on the ground in the ground networks. The ground networks also picked up the cloud flashes. What about this one? GOES 16 saw some electrical activity. GOES 17 didn't, and it looks like the LMA did see some flashes in this time window, but none of the ground-based networks did. So if we move forward in time, it looks like there's good correlation. 16 and 17 are seeing these flashes. The ground networks are detecting CGs and intercloud activity. And then we get to this flash. Well, again, it's low altitude like this one, which GLM saw, but there's no GLM detection. So when you look through all the lightning data, just remember that there's certain things that can impact it, be the sensors, the distance that lightning has to travel from the storm to the GLM, that could all impact what you're seeing. But if you look at it over an entire time window, and even though this is only 2 minutes, but if you stretch it out 5, 10, 15 minutes to an hour, that can help fill in a lot of the gaps. So how do I use this operationally? This is my WarnGen setup that I have on my center graphics monitor. It's very basic, WarnGen, half-degree reflectivity and velocity when I need it, so I can issue warnings and not have to worry about any cave issues. Next window to the right is my interrogation window. You can see that I keep up a all tilts panel of reflectivity, the base moments. Underneath that is the dual pole moments, but I always keep in the top left here and the bottom left the GLM data, flash extent density and average flash area. That gives me flexibility, so that way I can overlay the ground-based networks in here. I can change that to, or overlay with visible satellite, infrared satellite, any kind of mesoscale data that I need, surface observations. but this is also looping. And so even though it's in this top corner during, in that window when you're looping, it only shows 12 frames, I can quickly move it over into the main pane, and I'll have that set for 30, maybe even 60 minutes to be able to watch the trend with time and be able to pull out any information I can from it. When it's sitting over here on the left, it kind of just is an easy way to quickly glance over there and make sure that all the networks are giving me the data that I would like to see. If you notice down here in the bottom left, I had Earth networks data plotted in this window, but it's not there. So real quickly, I can look at that and say, something's not right. I'm seeing the data from the GLM. I'm seeing the data from the Visala network. I wonder what's going on. And what happened in this case is that that frame hadn't refreshed yet. The data was there, and I was able to watch it come in and then grab the data or the information I needed from those loops. So where does that leave us? Is the GLM perfect? No, but it's pretty good. We may not see everything in the individual flash data, and there are certain times of day where the detection efficiencies aren't, so that we may not see all the flashes. But overall, if you look at the trend data, it's there. The key thing is to make sure it jives with other information. If we're looking at the GLM with the ground-based networks, or even with some of the research-based networks like an LMA, are they looking like they're close to each other? And the other thing to remember, at least within AWIPS right now, until this next release of the Tower S package comes out, is that we don't yet have complete data in AWIPS. We're only looking at GOES 16. So once GOES 17 comes in there, especially for the central part of the US and offices there, you'll hopefully be able to get data from two sensors to be like, okay, well, 16 saw this, the GLM on 17 didn't, or vice versa. And I wonder what that could be that would impact that. The other thing that I want to stress is that outliers are rare, but they do happen. And this is important because if you see these cases, you need to say something. There's the Total Lightning Working Group within the National Weather Service. There's the GLM science team, and a lot of the professors and researchers that are on this team have accounts on social media. So if you see something that just doesn't add up, it's important to say something so that we can go back and look at this and see, okay, was it a sensor issue? Was it a processing issue? Was it something in AWIPS? And with the new release of the Tower S package coming out and GOES 17 data soon to arrive from the GLM, vigilance is needed. We've got to keep an eye on this. We need to make sure that they line up. Are we seeing things that match up or not? The last thing is that Corona sticking around, field forecasters and operational METs and those that are looking at this data all the time are more important. A lot of the things that we've learned about the GLM and its operational capacities and limitations have come through things like the hazardous weather testbed, the experimental warning program, testbed offices that are looking at the data before a larger release to the Weather Service. Well, coronavirus is pretty much going to limit those opportunities to have dedicated testing in places like the HWT with lightning data. So we, the users that are using in the field, are going to be more important to help find out if there are issues and then relay that to the people that are developing the data, processing the data to make sure that it's going to be handled. And so with that, I'm pretty well done, and we'll move into the questions.
Hey, Jason, appreciate that. Really good presentation there, some good information. First of all, of course, this is Randy and Norman. I just want to say thanks for the opportunity to help facilitate these questions. And if anybody does have any questions, feel free to enter those in the chat, and we can work through those over the next few minutes. Just go ahead and type that to us, and we'll go ahead and kind of run through those. But I guess to start things off, Jason, I know you talked about some of these issues with detection and data dropouts and other problems, and you kind of covered this, but I was just curious, just can you talk a little bit more about how often this happens, or is this something that's really common, or is it, just kind of how often do we expect to see those type of issues with the data?
From a meteorological perspective, it's not going to happen very often. You've got to have the right convective environment with the right storms producing a significant amount of lightning data that will cause the sensor to have issues. And then from a data processing perspective, that one is a little more iffy. The way that the data gets into AWIPS right now is that it's getting processed and this may be a little bit old, so I'm hoping I remember this right. It's getting processed at the Aviation Weather Center, and then that data goes out through LDM to the regions, and then from the regions to the office. And so at any point, if you have an internet cut, LDM goes down, or anything along those lines, the GLM data that we see in AWIPS will drop out. And that can happen a little more often than an actual issue with the sensor itself.
Okay, good to know. Let's see, Bradley has a question here about GLM, where to find it specifically in the AWIPS menus. And I'll just mention just real quick, I know that it's under the satellite menu, so it's not grouped together with the ground-based networks. I don't know, Jason, if you want to add anything to that, or if there may be any variance from one AWIP setup to the other.
That's correct. You have to have the Tower S satellite package installed, and you have to have the data coming into your system via LDM. If I remember correctly, because I don't have an AWIPS workstation next to me, if you go to the satellite menu, go 16, go 17, somewhere in one of those submenus is the GLM menu, and then you should have an option for flash extent density. And I don't remember if average flash area and total optical energy has been turned on yet for every office in the Weather Service.
Okay. Let's see, Pat asked about the perspective from a warning forecaster and was curious what the average flash area tells you as a warning forecaster. Maybe that's a little bit different from, say, convective warnings compared to maybe DSS for lightning. Can you talk a little bit about that?
Sure. I went back to this image because this is average flash area in the bottom. Two things to look at it from this perspective is that you notice here that these colors underneath the lightning flashes are in the blues and the purples. These are very small flashes, and these are usually associated with very intense updrafts producing a lot of very small flashes. And then if you transition into the stratiform rain region, you're getting into these warmer colors that indicate large flash areas. For instance, some of these were approaching 8,000 square kilometers in area. These are the large, for those of you that are storm chasers or watch when MCSs roll across, these are the anvil crawlers going out the back of the storm that just kind of finger out for long distances underneath. So from a DSS perspective, the thing to know here is that, okay, these small flashes in the leading edge of the storm is where my most intense convection is going to be, and will probably need to be watched for maybe convective warnings and things like that. When we transition back here into these large flashes, overall, this could be moderate rainfall and not a lot of lightning, but it's still possible that you can have lightning flashes that generate here in the leading edge and then transition all the way back out here behind the main convective line, dropping CGs along the way. And I remembered that I actually put in here an example of that from the GLM science team meeting 2 years ago. This is one flash that started here along the Red River and transitioned all the way into southern Kansas. So your average flash area on this is going to be, 4,000, 8,000 square kilometers as it produces lightning all the way up into Kansas, even though this flash started along the Red River. So, average flash area, if you're seeing large flashes directly, you still have a threat of lightning underneath that, even though the stronger convective updrafts could be almost a full state south of where you're at.
Okay, good information, Jason. That's really helpful to me. I know I continue to learn more and more about GLM, but this was very helpful. Let's go ahead and I guess we can toss it back to Brian for any final comments, and then after that, maybe we can stick around for a little bit longer. But for those that have to drop out, we want to go ahead and make sure that we keep on time. So, Brian, do you have any final comments?
Hey, Randy, thank you very much for facilitating this discussion. And Jason, thank you so much for this informative presentation on using the GOES-R series GLM and AWS operations. An enormous effort was put forth over many years, and it's gratifying to see it in use. Great information here, some things I had not seen before or had not contemplated before, such as detection efficiency and how to use GLM in conjunction with other data sources, ground sensors, and so on, such as the lightning mapping and others. So very, very much, very informative. Thank you. I want to call your attention to the feedback chat, feedback site. David has put into the chat session. If you're in the GoToMeeting now, you can see a little, it's not already visible to you, the chat bubble. We encourage you to fill out that survey, short survey. It'll help us improve these presentations in the future. And as you can see also up on the screen, we want to encourage you to join us 1 week from today on Thursday, October 22nd, where Ravon Amadov from Ceres is presenting to us a presentation on high-resolution predictions for smoke visibility, smoke weather interactions using satellite bioradiative powered data. And like this GLM talk today, what could be more relevant? Definitely looking forward to that, and encourage your participation in that. And then I guess we want to thank you all for joining. And although we're concluding the formal part, if you will, of this segment of today's book club discussion, we want to encourage you to remain on. Jason, with Randy's facilitation, can perhaps provide further insights and answer any questions you might have. So thank you very much. And Randy, back to you.
All right, thanks, Brian. Yeah, there's a few more questions coming in. So yeah, if anybody can, if you have to hop off, that's of course something continue to have a little more conversation here. But there was a question about the minimum flash area, and they were asking about, kind of that it would be coming eventually. I know you mentioned that, but that if it would eventually replace the average flash area, and then they wanted to know a little bit more about kind of the significance of that product, the minimum flash area.
Sure. I'm not entirely sure. I think it's going to replace, and I know that folks with Tower S are on here to correct me if I'm wrong, but I think it will. And the reason that the minimum flash area was added in is when you're looking at average flash area, it's kind of hiding some more of the information that you could get early on. When you start getting storms that develop, usually those flashes are going to be very small, and so by doing an average flash area, it probably would be weighted more towards the larger sizes of the flashes. So with minimum flash area, you're going to be able to pull a lot more of that information out early on. And then the second thing is that it will help kind of when you're looking especially at the large stratiform flashes. Again, that's going to weight it more towards the larger portion of those. And so hopefully minimum flash area is going to be able to pull out a little bit better where you're starting to transition from the leading edge to the convective line into the stratiform region, and some of those size sorting that takes place with flashes as you're transitioning into different types of storm environments and where they are in their life cycle. I guess is a better way to say it.
Okay, good information there. There was kind of another comment from Michael that mentioned that kind of the situation if you're out in the oceans and you don't have other data to sort of confirm with GLM, obviously it's just you have GLM data only. You may not have radar data and ground-based lightning data. So maybe talk a little bit about just using GLM data by itself without the context of other data to help, sort of complementary. That's interesting.
Yeah.
I've never really thought about that too much.
And it's a great question. I think that especially in the equatorial regions where you're pretty much almost underneath the satellite, it should do very well. There will be cases again where maybe you have super intense convection that the flash rates reach towards the top of what the sensor can process in events per second. But overall, I would say that over the oceans until you get maybe in the extreme northern or southern parts of the oceanic basins underneath the GLM, fairly confident that that data is very good, especially more so at night, obviously, because you're going to have better transmission to the satellite. So I'd say that confidence in using it underneath, like I said, in the equatorial regions would be fairly high and very good. The other thing is that in AWIPS, you should still have some lightning data to compare it to, at least with Earth Networks and the Visala GLD data. There are limitations on the latitude and longitude for those data sets, but it does cover a large part of the oceans in order to help out the OPC and WPC and HC, a lot of the centers that are looking at that data for what they need it to. So that way you could at least get some comparison in there.
Okay, and I see that Nick down in Jackson made a comment about the average flash area it's not been activated all sites yet. So then there was, kind of maybe this idea that, let's see here. Yeah, that if that's the case, then certainly contact the Tower S team and they can resolve that. There was a comment by Steve also that talked about how I guess the idea of the MFA was sort of to create an emphasis for CI. The flashes are small and it's kind of a little bit of a strategy there, I guess, with MFA. Let's see here. Another comment. So I'm just kind of reading through the comments here. Let's see, Brian down in Midland, he was saying that MFA might be used in concert with radar to depict updraft intensity. So he was asking about that. Is there a correlation there?
Where your most intense updrafts are, that's where you're going to have most of your mixing taking place along the edges of the updraft and a lot of charge separation taking place. And so with the smaller flashes, you should be able to see, especially in very robust convection, a correlation with the minimum flash areas being located near those updrafts. Now you got to remember that you've got to take into account parallax. There's going to be some offset in the location of the GLM data to the radar data, and this is something I've seen in operations a lot. But yes, when your updrafts are super strong and super intense, you should see a lot of small flashes in and around that. And then as you transition, say, into a dissipation phase and that mixing is kind of weakening or decreasing, and you start to see larger flashes, the location of the minimum flash area may start to see the sizes get larger. And then I know there was a case when I was at the hazardous weather test bed in 2019 that there was new convection developing underneath an anvil in the Texas Panhandle. And the average flash area that I was looking at, because I wasn't there to test minimum flash area, unfortunately, did see a decrease in flash areas as that updraft made it through the anvil. And so you'd have this large area of large flashes, and then all of a sudden this little pocket of small flashes showing up associated with that new convection.
Okay. Yeah, I don't want to speak for all forecasters, but I'll just kind of tell you where I'm at with it now, just overall GLM. And I don't have nearly as much knowledge as you all do, but just to sort of speak from the forecaster just a little bit more, I kind of want to talk about that. I've really, I've obviously found it very useful, the flash extent density especially, but I haven't really gotten too much into some of the other products. Continue to learn about that. I think obviously these type conversations are excellent for exposing forecasters to that and giving us the opportunity to learn more about the power of GLM. But one thing I had is kind of a question to add to the conversation a little bit is, you mentioned about being closer to the equator, being obviously much higher quality data. And then I was really struck by the maps that you presented about the northern plains and the northern Rockies, say Montana and North Dakota, how much, this obviously from just a satellite perspective overall is some challenges if there are parallax and whatnot, but GLM as well. So if I were working at the office in Glasgow, for example, one day, and then I would go to the office in Tucson the next day, how much, in sort of a qualitative sense, how much of a difference would I notice in the quality of the GLM data from those two locations?
Pretty significant, because Alaska is so far north that you're getting on the fringes of the GLM itself, and so the difference in detection efficiencies, I'm going back to my maps, the GLM can only see as far north as the Aleutians on GOES 17, and so if you're looking at data there, the detection efficiencies at night are still around 40 to 50%. And then if you move to the southeast, or excuse me, to the southwest US, like you said, Tucson, you'll notice that the GLM is seeing a lot more of the flashes, just because by the location and perspective of the sensors to that location, your detection efficiencies jump up closer to 80 to 90% at night on the GOES 17, and then 70 to 80% roughly during the daytime. So that is a very good point, that as you move across offices across the US and the globe, actually, since you could go to Hawaii or Guam or our friends in the Pacific region, this GLM will show you different amounts of data just by the nature of the detection efficiency in there. So it's something to keep in mind. And I lament, excuse me, I lament that we really don't have a good way to show real-time detection efficiency from any of the lightning networks, GLM, the ground-based networks, to know how well it's performing at any given time.
It's good to know. William down in Key West had made a comment saying that that they don't always have the best coverage as far as the ground-based network, so they found a lot of value obviously in the GLM in the Florida Straits area down in South Florida. Let's see, anybody else have any comments or questions? Keep kind of watching as they come in here. Let's see. Yeah, all right, interesting. If anybody else has anything, feel free to type it in there, but I may toss it back to Brian and see if Brian has any final comments as we start to wrap the informal discussion up.
Nothing more from here. I guess we can thank again all the participants, mentors, and Weather Service, and other listeners, Bartlett Institutes, for your participation in today's seminar and all of the work that's gone into the GLM over these years. It's really gratifying to see it working in operations, and still learning a lot more about it. Its full potential not yet realized. So I think with that, we can conclude today's session and look forward, as we said earlier, to seeing you next week. Any issues, as you can see on the screen, with installing the RPM, the Tower S team, John Lee and David, will gladly help with bringing the software up to date so that you can exploit these data. So thank you very much, everyone, and enjoy the rest of your day.